Hi everybody, and welcome to example 5 on page 40 of the workbook here. This is going to be our first example of actually calculating a null space and a range of a linear transformation, and in particular, what they'd like us to do is to find a basis for the null space and the range of this transformation. Okay, and it turns out that there's a nice process for doing this. Okay, we can kind of streamline this. So the first example that we do will take us a little bit longer because we kind of need to discover a few things. Okay, and then after we have this example behind us, we'll have kind of a nice way to break this down and do this in a more efficient way. All right, so let's look at part A together here. So they're giving us a linear transformation from R4 to R3 that's given by this formula. Okay, and let's start with the null space. See if we can find a basis for the null space. So we first need to remind ourselves what the null space is. Okay, it's the set of all vectors that we can substitute into our domain that give us out the zero vector. So it's like saying we're going to take this output and set it equal to the zero vector in R3. Okay, and we're asking, what are all the values of x1, x2, x3, and x4 that would make that a true statement? Okay, well, what's interesting about that is what this is really saying is that we need three equations to be true. We need x1 plus x2 minus x3 plus x4 to equal 0. Okay, if we put that into a matrix, it would look like 1, 1, negative 1, 1. Those are the coefficients equal to 0. That's one equation that has to be true. Then we need x3 plus 2x4 to equal 0. Okay, notice that there's no x1 and x2, so we're going to get 0x1 plus 0x2 plus 1x3 plus 2x4 equals 0. Okay, and then finally, we need this equation to be 0. Okay, looking at the coefficients, that means that we're going to get a 0 there. And then, or sorry, nope, that's not right. Back up. Okay, 2x1 gives us a 2x1, 2x2, 0x3, and then 6x4 equals 0. Okay, so to find the null space, we're looking for the set of solutions to this system. Okay, and we know how to solve systems of equations. We just do row operations here. Okay, and I'm trusting by now you can either do this by hand or do it on your calculator or on an app or something. If you do that, here's what the system could look like if you reduce it. Okay, like that. All right, and to actually get our solutions, we need to sort of identify where our pivot positions are. So we've got one there. That's the first non-zero entry in the first row, and then one more there. Okay, so how many free variables do we have here? Okay, notice that there are two. Those correspond to the two columns that don't have a pivot position in them. So here and here, x2 and x4 appear to be our free variables. So let's give those names. x2 is equal to t, and x4 is equal to u. All right, now that we've nailed down those free variables, let's see if we can solve for the other two variables. Okay, so going back to our system, I'm going to start with the second equation, which, if we write it down, looks like x3 plus 2x4 equals 0. Okay, and if we take that and solve it for x3, we're going to get x3 equals negative 2x4. And we know that x4 is u, so we're going to get a negative 2u. There's the value of x3. All right, and then back up to the first equation. If we write that one out, it looks like x1 plus x2 minus x3 plus x4 equals 0. And we'll solve that for x1. Let's see, negative x2 plus x3 minus x4. Okay, we'll go ahead and sub in the values of the variables that we know here. So let's see, x2 is equal to t. So we're going to get a negative t, and then x3 is equal to negative 2u, looking above. And then finally, x4 is equal to u. So we'll get a minus u. And if you simplify that, notice that you get negative t minus 3u. Okay, so we've managed to find values for x1, x2, x3, and x4. So we can describe our null space then. So therefore, the null space of T is just the set of all x1, x2, x3, x4. Let's look at what our values are one coordinate at a time. So x1 is negative t minus 3u. So that's what goes in our first coordinate. Then let's see. Next up is x2. That's equal to t. Okay, and then x3 is equal to negative 2u. You can check that. And then x4 is equal to u. Okay, so that's the null space of T. That's our solution to this system of equations. And if we pull that apart, this is the same type of calculation that we did back in the last section. We can rewrite this as a linear combination by noticing that it's equal to T times negative 1, 1, 0, 0 plus U times negative 3, 0, negative 2, 1. Okay, and so what does that say here? Okay, well, I'm going to make a claim here. I'm just going to write it down and then we'll pick through it together. I claim that beta, and I'm going to call it beta of n, that n means null space, negative 1, 1, 0, 0, and negative 3, 0, negative 2, 1. I claim that that's a basis for n of t, and that the nullity of t is equal to 2. Okay, now I kind of said a lot there without explaining any of it, so let's go back and see why we're saying all of that. First of all, how do we know that this set is a basis? Okay, well, the two properties of a basis are the vectors in here have to span the null space. Notice that that's true because of the calculation that we did up here. We demonstrated that the null space of T can be, everything in the null space of T is a linear combination of those two vectors. The other property we need to have a basis is linear independence. And the fact that these two vectors are not scalar multiples of each other tells us that they're linearly independent. Okay, so we're just putting those two facts together. Okay, and then what about the nullity of T equals 2? Well, what was the definition of the nullity again? It was just our name for the dimension of the null space, and so the fact that our basis has two vectors in it tells us that the nullity of T is 2. That's the dimension, okay? And so we've answered half of this question. We've got a basis for the null space, and we've got a nullity. Okay, the other thing that we wanted to do was kind of the same thing for R of T. Okay, so find a basis for the range and figure out what its dimension is. Okay, so let's see if we can tackle that problem below here. All right, and this is going to take some space. So I'm going to write R of T way over here to the left. Start by reminding ourselves what the range of T is. It's just the set of outputs. Okay, so this thing that I'm circling up here. So we could write that as the set of all x1 plus x2 minus x3 plus x4, x3 plus 2x4, 2x1 plus 2x2 plus 6x4. Okay, where x1, x2, x3, and x4 can be anything. Okay, and that's just our definition of the range. Okay, and notice that we can pull that apart. This is the same kind of calculation again that we did back in section 1.6. If we did that, we could break it up like this. Okay, I'm going to ask you just to confirm this, okay, on your own algebraically. This is really true what I'm writing here. Times 1, 2, 6. Okay, and again, x1 through x4 are anything in R. But notice that by writing it like that, R of T is the span of 4 vectors. 1, 0, 2, which actually appears twice. Negative 1, 1, 0, and 1, 2, 6. Okay, now, do you recognize the 4 vectors that are kind of sitting there? Those were exactly the columns of this matrix up here. Okay, and that's a very important observation. I'm going to make it down here. So, columns of coefficient matrix above. And we already know from the previous section that if we want a basis for a span of a set of vectors like this, what we can do is just form a matrix where those vectors are the columns. That's exactly what we did up here, do row operations, and then take the pivot columns. So we know, without doing anything else, that a basis for that span is just going to be obtained by taking the two pivot columns, okay, which are the first and the third in this case. All right, so putting that all together, we can say, therefore, a basis for the range is just going to be the first and the third vector. That's what our matrix calculation above tells us. Okay, the pivot columns form a basis for R of t, and the rank, that's just the dimension of the range, then has to be 2 because there are two vectors here. Rank of t equals 2. All right, so just to summarize then, what we've kind of discovered in this example is that answering both of these questions, finding a basis for the null space and the range, can be done by starting with this system of equations. That's going to be our strategy every time we do a problem like this.